Hello and welcome to Easy Projects. So today I want to get started with the constant current load that I have been talking about. And I have written constant current because I really wanted to do pulse current and ramps as well, if that is possible, but we will take a look at that later when we get to the software part, because I am going to make this Arduino controlled. And except for the latest video, this will also be the first time that I actually use an Arduino on the block here. I have been playing around with the Arduino myself a couple of times, but I have never really made a larger project with it. I want to try that now. So that is the reason that I chose to do that. I already have one constant current load that I made over 2 years ago. And the reason that I want to make a new one is that this doesn't take very much current, and also this input side over here, I've just used some diodes and some pins. And that is just very annoying, but I didn't think about that at the time. And also this is not very precise at higher currents. The reading on the display is a little bit high, and these resistors get burning hot. So that is some things that need to be corrected. Even though there is a PIC microcontroller on this constant current load, it is actually analog controlled by this potentiometer. And the only thing this microcontroller does is to read the voltage drop over these resistors with the ADC and display it on the display here. And yes, that is quite overkill to use a PIC16F877, but that was the only microcontroller that I had with an ADC at the time, and I had a whole bunch of them, so I just used that. But yes, if I had to do this today, and I have, I would definitely not make it like this. But when all that is said, the working part of this circuit, the thing that actually regulates the current, is identical to what Dave Jones from the EV blog used in his video when he made his constant current load. So yes, I have stolen it. But that actually works pretty good, and I am going to use that in the next one as well. I'm just going to use more of these MOSFETs and a larger heatsink, of course. So let's start by taking a look at the requirements for my new unit here. First of all, I want it to be in a box, so things and stuff can't fall on to here and short everything out. Not that that actually happened, but of course it could happen. And next I want it to be powered from the mains 230 volts, because in this one I have to come in with a battery and an alligator clip or something and hook it onto this diode and this ground pin here, and that just doesn't work. I want it to do from 0 to above 5 amps, so I just 0 to 8 amps. This sounds good. And of course it's also about how much voltage you feed in here, because that will kind of determine how much power it will need to dissipate. But we will get back to that later. And I want it to be at 1 milliamp resolution. That will be good enough. And also, very importantly, I want it to accept banana blocks, and it should have binding posts. Again, so I don't have to hook alligator clips onto here, because that is just annoying. And I might add a rotary encoder. I don't know, I will see how it will work out with the buttons, but that decision could also wait. And I want to have the power button on the front, because on the power supply that I built myself I have the power button on the back, and that is actually pretty annoying as well. I didn't think about that at the time, but we learn every day. So this circuit is what will be the working part of the load. And the way it works is pretty simple. We have a DAC here that will feed in a voltage from 0 to 4.096 volts. And this is the reference that I have, a voltage reference. This signal will be fed into the non-inverting input of an op-amp, and this op-amp is configured as a non-inverting amplifier with a gain of 2. And the gain is set by these two resistors here. So the op-amp wants to see the same voltage at this pin here that we set on this pin up here. And to accomplish that, it will adjust the output here. And the output is connected to two N-channel MOSFETs. Or it could be 3 in the final design, I don't know. I'll have to play around with that. Into the drain of these MOSFETs we have connected the load of the device that we want to draw current from. To the source is connected a balance resistor. This is just 0.1 ohm. I don't know if this is actually needed, but it definitely will not do any harm to put them in there. After this, the traces are joined again, and they go through a single 1 ohm resistor to ground. And this resistor will not be 1 ohm in the final design, but we'll get back to that. We also feed this voltage back to the op-amp, but through this voltage divider here, and this is what divides this voltage by 2. So whatever voltage we set at this pin, we will see double that voltage at this point here. And using Ohm's law we can easily calculate how much current that will allow through this resistor. And that is how we can control the current in this circuit. And we also read this node here, the ADC, to confirm that we actually have the current across this resistor that we chose up here. So the reason why I cannot use a 1 ohm resistor here is that the constant current load have to be able to draw 8 amps. And 8 amps across a 1 ohm resistor is simply too much power. And I would need a very large resistor, but we could do that. But the problem is that in order to allow 8 amps through it, we will need 8 volts here. So we will need more than that up here. So that basically means that if we don't have 8 volts at the input, we cannot draw 8 amps. And I want to draw 8 amps at 5 volts, for example, or even 3.3 volts. And that simply cannot be done with a 1 ohm resistor. So I will probably choose a 0.1 ohm resistor and then divide this input signal by 10 with another op-amp. And that should work exactly the same. The reason why I chose this to begin with is that I want to test it in the breadboard. And if I put a 0.1 ohm resistor here, then it will simply not work in a breadboard because there's both resistance in the wires that we use to connect things, and there's also contact resistance. So we could easily have perhaps 1 or 2 ohms between this resistor and ground. If this signal is divided down by the factor of 10 that we need if we use the 0.1 ohm resistor, then we will only have 0.4 volts at this input, so 0.8 volts at this node here. And if we have all that resistance, well, then we can't draw any current, so it basically won't work. But I am also fairly confident that I can test it in this configuration, and then change the resistor and divide the signal down, and then it would still work. That could of course introduce a problem or something, but at least then I know where the problem is. And the digital circuit and the Arduino software we'll take a look at in another video. I have made some of the software and I've built this up on a breadboard, so let's take a look at that. So here is the circuit that I have built up so far, and you must excuse the wire mess. I tried to keep it nice and tidy, but as you see I didn't succeed. But there is a lot of stuff on here, so I use that as an excuse. Yeah. But what we have is the Arduino. That's this guy up here. Well, it's not really an Arduino, it's a clone, but it works the same way. We have an LCD screen. We have the ADC over here, the DAC here. We have the contrast control for the display here. And we have a transistor to control the fan here that I added. We have 4 buttons here to control the thing. The voltage reference is this guy here. The op-amp is this one here, and the 2 MOSFETs are mounted on this heatsink. And we have a temperature sensor in here. I only had one 0.1 ohm power resistor, so I used 0.47 ohms instead. But I still used a 1 ohm for the main sense resistor here. The value of these doesn't really matter for the performance, but the greater these values are, the more voltage you will need at the input in order to make it draw the full 8 amps. So I don't know if it makes any sense to show a close-up of this breadboard because it is really a mess. But what I did is I tried to keep all the important signals as low impedance as possible by using these solid wires. And for the not so important signals I just use the regular breadboard jumper wires like this. These are rubbish really, and a single wire can actually have over 1 ohm in resistance. I've measured a few of them. Some are like 0.1 ohm and others are like 1 ohm, so these solid core wires are much better in that respect. But there is still some resistance in the contacts in the breadboard. And I think if you have a real quality made breadboard, it would be better. These are just some cheap Chinese ones. But anyway, I wanted to have as little noise on the output of the DAC and the input to the ADC as possible. I also added a lot of bypass capacitors, like everywhere. And this really makes a huge difference. When I first just connected it up with these jumper wires, the ADC readings were just all over the shop, and now with this improved setup I can actually get some fairly stable readings from the ADC. It's not perfect, but it is now within a few milliamps, so that is good enough for this breadboard test. So let's try to fire up the circuit and see what I have got working so far. And I'm sorry my power supply is a bit loud, but I hope you can hear what I'm saying anyway. So let's turn it on. And we can see the LCD has turned on over there. So I have added this mode select menu because, as I said, I wanted to do constant current, pulse current and ramp currents if possible. But I have only made the constant current part yet, so there is only the constant current and a setup. So if we take a look at the setup to begin with, we can adjust the backlight and steps from 0 to 255. I just made it so that it will take 5 each step, because you can't really see the difference anyway. So, and we can just hold down the button and it will change. And we can take the next one. And I added a fan here, as I said, and we can set the start temperature. So if I set this to 20, it should start up. Oh, sorry, you can't see that. But if I set it to 20, it's going. If I turn it up, it stops. And I have made it so that it doesn't just turn on full power when it turns on. It just slowly ramps up. So if it gets to the set temperature, it will turn slowly. And if the heatsink keeps rising in temperature, the fan will spin up. And when it is about 7 or 8 degrees Celsius, I can't remember, above this value, it will be spinning at full power. So we can set that. Let's put it back to 30. Let's take the next page. And I have added a safety cutoff temperature. So if the temperature gets above what you set here, then it will just turn off the load. And that's it. I don't know, maybe I will put a few more options in there. I will probably need something for calibration and stuff like that, but I haven't got to that yet, so that has yet to come. But if we take the constant current, then we can first choose the digit that we want to change, and then select one. Or if I say we want to set 1 amp, we can do that. Then I don't actually know if I like this feature, but I have made it so you have to click all the way through to start, so you don't accidentally press start and blow something up. But perhaps some people, or myself including, will find that annoying, but I'll see. Maybe I'll change it so that I have a dedicated start and stop button. And we can start that. And as you can see, it reads a bit low. And that is actually because there is more than 1 ohm of resistance between the measuring point here and ground, because the ground reference is all the way over here at the deck. And You can see the fan just started there. If we take a look at the power supply, it kinda agrees with the display down there. If I just turn off the load again, we would expect to see about 130 milliamps or something. And it's close, so. I haven't calibrated it or anything yet, so I didn't really expect it to be spot on. And when I turn off the load, then the fan should stop again very soon. And there we go. So this was about it for this first video. And as I said, I will do a video on the software and the digital part. And I will also do a video on the enclosure or housing for this whole project. And I have a little surprise in that video. So you have something to look forward to. And actually one thing that I haven't told yet, I have got myself a new camera. So you can see the old one that I used to shoot with is used to hold the LCD display over there. If you remember, I had a lot of problems with the audio, and I tried all different things with plugging in external microphones, and nothing really seemed to help. Well, I did manage to get one thing working, and that is this studio microphone that I have. I have bolted that onto the shelf there, and I recorded a few test videos with that, and it was a little bit better than any other external microphones that I've tried. But it was really just in the way, and I had to use this audio interface or preamp or whatever you call it up there for it to work, and I had to have wires going all over the shop, and it was just messy. So I decided to buy a new camera. And I got the Canon HFG30, and I really like this camera. It's worth every dollar and cent, I think. And I am just using the internal microphone in this camera, and the audio quality is just way better. So yep, well, I might do a review of the camera, but I don't know. If anybody wants to see it, then you can just put a comment below, then I will do a video about the camera. But anyway, if you like this video, please give it a thumbs up and subscribe to my channel if you're not already a subscriber. And thanks for watching, and I'll catch you soon for the next part.